Okay, so far what we've been discussing is sort of the nonlinear interaction between optical fields which are freely propagating, right? So either they're beams in free space or traveling through some fiber or waveguide, but they are propagating fields, right? Um, Today we'll discuss what happens when we have fields inside an optical cavity or resonator, right, where light is bouncing back and forth between mirrors and it stays confined in a small region of space. Right, a cavity or a resonator is basically something that stores energy for some time. So we'll see if you have, for example, a nonlinear medium inside an optical cavity, what kind of effects we can get. Okay. So the simplest cavity that one can consider is like a fabric arrow cavity, right? So you have two mirrors at some distance L apart, right? And let's say these mirrors have reflectivity R. So both of these have the power or intensity reflectivity R, or if we want to define the reflection coefficient in terms of the electric field amplitudes, then we can say it's small r, and the intensity and amplitude reflectivities are related by the squares, you know from your basic optics, right? Okay. And then let's say that the cavity is filled with a medium which has a third order nonlinearity type 3. Okay. Okay, so the way we can analyze it is how we usually analyze, let's say, a fabric arrow cavity, which you might have seen in your basic optics courses, right? So let's say I have some incident field with amplitude A1. Okay, and then let's say the field inside the cavity. So just after the first mirror here, let's say it's A2. Let's call the transmitted field as A3. Okay. Of course, there'll be a reflected wave here, right? So we can call that A1 prime, let's say. Okay. So, yeah, we can define a transmittivity for these mirrors, which is 1 minus R, or a small t for the amplitude transmittivity for each of the mirrors. Okay. So we know that so of course A1 prime, the reflected field is just R times A1, right? It's just the reflectivity of the mirror. Okay. Oh, sorry, small r, because A's are the amplitudes, the electric field amplitudes. Right? And then in steady state, if we want to look, let's say, see what is the field A2. Okay, so we can write A2, the field inside the cavity. So of course, it has a portion which is just a transmitted portion of my input field, right? So that's T times A1, right? Plus this field is also circulating in the cavity, right?
So, what do you mean by steady state?
Steady state means like, so you turn on the fields and typically it takes some time for the fields to settle in, right? So because you'll see that basically the photons which enter the cavity, they can either go reflect back, right, and stay in the cavity, or they can be transmitted outside, right? So when initially you introduce the first few photons, some of them will go, some of them will come back, and it will take some time for the energy in the cavity to build up, right? And after that, if everything is constant, it will reach some steady state, so nothing is varying with time.
So we can say that equilibrium is maintained between the input flux and the output flux.
Yeah. So I mean, if my input is a CW wave, so it's constant with time, then of course everything will become eventually constant with time. But let's say if I turn on my field at some point t equal to 0, you'll see that like A2 or A3, it will have some time constant before it settles to its final value. And that time constant is again related to sort of the mirror reflectivity, the losses in the cavity, right? So the finesse of the cavity or the Q factor of the cavity determines. So this is sort of something like the photon lifetime in the cavity. But so we're saying just ignore the dynamics and look at the steady state. Yeah. So yeah, one component is just the input, which is transmitted through the mirror. But then this field is also circulating in the cavity, right? So, basically, after this, I have to add basically the field which entered, let's say, one round trip ago, right? And then traveled one round trip here. So it went here, got reflected from the mirror, came back, got reflected from the mirror again, right? So there are two reflections from the mirror, one here, and then there is a phase acquired, which is the round trip phase, right? So that phase I have to include here. So phi is the round trip phase. Acquired by the field in the cavity, right? So this is sort of, you're saying that the field which is entering at this instant, this is the field which entered like one cavity round trip time ago, right? Similarly, there is a component which comes in, gets reflected again, gets reflected again. So 4 reflections, right? 2 round trips. So that will be r to the 4th. And then the phase will be 2 phi, 2 round trips. Right, and similarly, you can see you'll get an infinite series. Right, so next one will be r to the 6 e to the I3 phi to infinity. Right, so that will be the steady state if you include till infinity. Right. So this series is easy to sum. It's just a geometric progression, right? So I can write this as EA1 divided by 1 minus r square e to the I5, which is the ratio of the geometric progression. And small r square is just, we can write it as capital R. Okay, so that's the solution for the field in the cavity, steady state. And this round trip phase, so usually the round trip phase is just the, like the linear phase, the e to the ikz phase, which is acquired, right? So that will be this linear phase shift, right? So omega naught by c, n naught is the linear refractive index of the medium here. And then 2L is the round trip length, right? So that's the linear, the usual phase shift that is required. But if this material has a nonlinearity, so chi3 or equivalently a nonlinear refractive index N2, then you know that there will be a self-phase modulation phase shift also, right? Which is proportional to the intensity, right? So that will go as 2 omega by c, then N2I L, right? So this N2I2, what is the intensity? That's I2, which is the intensity inside the cavity, right? Because the field inside the cavity is the one which is acquiring the phase. So this I2 is the intensity inside the cavity, which is so that's just proportional to A2 square, right? Mod A2 square. So A2 is the field inside cavity, I2 is, so this is the linear phase shift and this is the self-phase modulation. That happens. So now, let's say we want to see what is the intensity inside the cavity, right? So that's proportional to mod A2 square, right, with some constant multiplication. So when you take mod square, we can take mod square of this, right? And that constant which comes outside can be absorbed into mod A1 square, right? And I can just write I2 as T square I1 modulus of this denominator here. Right, and then T square is just the power reflectivity or power transmittivity T. And then mod square of this is basically, so it's a complex number, so this multiplied by its conjugate. Right? So you can see that I2 by I1, which is basically the factor by which the field is enhanced inside the cavity compared to my input field, input intensity, right? So this is the enhancement factor in the power or the intensity. So this will be T, the denominator will become 1 plus R square minus 2R cosine phi. Right, so you get a e to the I5 and then e plus e to the minus I5, which becomes cosine. Okay, and then we can use this trigonometric rule, cosine phi is 1 minus 2 sine square phi by 2. Okay, so this I can write as, so from the 1 I'll get 2r here, so that will be 1 plus r square minus 2r, which is 1 minus r whole square, right? And then this other part will give me 4r sine square phi by 2. Okay, and 1 minus r is just t, right, by definition. So this is just t square, first term. So we can divide numerator and denominator by t square, and so we can write this as 1 over t by 1 plus 4r square by t sine square phi by 2, right? Where phi I can write it as some phi naught, which is the linear phase shift, which is independent of intensity, right? So that's just I can call some phi naught. So this whole thing some phi naught. Plus the second term is something proportional to the intensity I2, right? So I call that constant kappa. So basically I get this expression for I2 by I1, right? So 1 over t and then 1 plus 4r square by t sine square phi naught, which is the linear phase independent of intensity, plus something proportional to intensity. So this is the same form. I mean, in your basic optics course, when you discuss the fabric arrow cavity, basically you do the same thing. You just don't include this nonlinear phase, right? So this. But now, since the phase can also have intensity, so I have intensity here, also intensity here. Okay. And if you want to look at the transmitted field, so the field coming out the other side of the cavity, so that's just the field inside the cavity. So I3, the intensity coming at the output is just T times I2, right? Transmitted through the other mirror. So you can see it's the same form. This T 1 by T just becomes 1. Right? So you can also write this as I3 by I1, for example, is equal to, you get 1 here, and then you can write I2 as I3 by T. So that will again be a constant. So both I3 and I2 have this form, or maybe I just write it explicitly. So I3 right? So I can write it like this. So this again has some constant by 1 plus something times sine square phi naught plus something times intensity. So both the field in the cavity and the field transmitted from the cavity, which you can measure more easily, right? Rather than the field inside the cavity, you can, the transmitted field is easier to measure. So that also has this same form. Okay, so then what will happen? So you know that in the usual case, right, when this material is just linear, we get resonances, right? So in the transmission, we get peaks. Whenever the round trip phase becomes a multiple of 2 pi, Then we get constructive interference in the cavity and the field builds up, right? And then we get a peak in the transmission. Right, so if I graphically plot this, so typically, yeah, in a linear medium, what is done, of course, so this chi3 is neglected, so N2 is 0, right? So this term is not there. You just have the transmitted intensity as a function of this phase phi naught, right? Which can depend on the frequency or length, right? So as you, for example, change the input frequency or change the cavity length, what you see is resonance, right? So basically, whenever this phi naught is a multiple of pi, this term goes to 0, and then you get a peak in the transmission, right? Now, in the nonlinear case, what we can do is, so let's say we keep the frequency and the length of the cavity fixed, right? So usually in the linear case, this is the x-axis is phi here, phi naught, right? Which is you vary either frequency or length, and you get these peaks. So now in this nonlinear case, what we'll do is we keep the frequency and the length of the cavity fixed. We just change the input intensity. Okay. So as we are changing the input intensity, of course, the intensity in the cavity changes, the intensity, and which also changes the output intensity, right? So if I plot the x-axis as a function of I3, okay, which sounds strange at this point because so I3 is sort of the output, but I'm taking the x-axis as I3, but just bear with me. Right, so basically we want to see what happens or what are the solutions that we get to this equation. Right. So this basically you can see is something like a transcendental equation. Right, it's not straightforward. It has I3 on the left side. It also has I3 on the right side, which comes inside this sine square. Okay. So one way to see what is happening is graphically. So we can plot both the function on the right hand side and the function on the left hand side, and see where they intersect. So the function on the right hand side is basically the function of the fabricator cavity, right? The usual function. And as I am varying I3, so that's basically I'm varying the argument of the sine. So basically I'll get same thing. It's like varying the frequency or length in the linear case, right? As I'm varying I3, I'm varying the angle here, and whenever this angle becomes a multiple of pi, I get a peak. Right, so as a function of I3, we get peaks. So that's the right hand side. And then the left hand side here is just I3 by I1. So as a function of I3, that's just a straight line with slope 1 over I1. Right, so that's just, if I want to plot here, it just looks like a straight line, right? So this is the right hand side, and this is the left hand side. So this is I3 over I1.
So in this graph, what we are plotting on the vertical axis?
Right now, I'm just plotting this function. Right, so I'm just vertical axis is just the value of, so in this case I'm plotting, so if I call this thing y1, this is y1 as a function of I3, right? So this thing I can call y1 as a function of I3, this function. So that's what I'm plotting. Then here this one I can call y2 as a function of I3, which is I'm plotting on the same scale. Okay.
Okay, sir.
It's like how do you find a solution to something like x is equal to sine x? right? One way to do it is graphically. So you plot the two functions. So one function is y is equal to x. That's just a straight line. The other function is y is equal to sine x. We call it y1, y2. So you plot sine x also, and you see where they intersect, right? And that's my solution. At this x naught is equal to sine of x naught, right? So that's what I'm doing. Okay. So basically, wherever these two curves intersect, that will give me a solution for I3. Right? That will satisfy this equation. So this straight line, the slope is 1 over I1. Right? Slope is 1 over I1. So, and I1 is my input intensity. So when the intensity is low, this slope is large. So it's very steep. Right? And then as I increase my intensity, the slope becomes lower. Right? So this is for increasing I1. Right? As I'm increasing my input intensity, the slope 1 over I1 is decreasing. So we can see, so for low intensity, I get an intersection here. Right? So the solution will be that value of, so this will be some I3A. Right? And then I change my input, increase it a little bit, then the slope reduces. So my solution shifts to here, which is I3B, let's say, right? But you can see at some point, it goes over this resonance, which means I get more than one intersection, right? So in this case, I'm getting an intersection here, 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 right? So for this particular intensity, there are actually three solutions, right? As long as the slope was steep such that it didn't intersect the resonance, it was only intersecting this lower part here once, so I got only one solution. But as the slope becomes lower, at some point I start getting three solutions, right? So in this range, when the slope is here, it will intersect the resonance twice and here once. So I'll get three solutions. And then if we further increase, then eventually it will go lower here. And then again, I'll go back to only one solution here. Right? So, now, basically, I can try to plot what I'm interested in. So let's say the transmitted intensity I3 as a function of my input intensity I1. Right? So for low intensities, the slope is high. I'm getting an intersection here, and that value of I3 is small. Right? It's here towards the left. So I start from here I1, and I'm increasing I1 here. So as I'm increasing I1, this slope is decreasing. So initially for some range, I'm getting only one solution. So I plot the solution here I3. So I'm getting something like this, right? So I3 is slowly increasing as I'm increasing I1, right? So this intersection point is slowly moving forward. Then at some point, suddenly what happens? I get three solutions, right? So in some range, suddenly once you pass a certain input intensity, you start getting three solutions. So that's represented something like this. Okay, and then once you cross this region, then eventually again you come back to one solution. Okay. So in this region you have one solution which is here. In this region also you have one solution which is here. In between here you have three solutions. So for each I1 I'm getting three values of I3.
Sir, but for lower slope lines, there will be other intersection of the another curve, so there will be more intersections. Why are we not considering them?
Yeah, so I mean, if it intersects another one here, you could have even more solutions. But let's say we consider only one resonance for now. Right? Let's say I don't know the FSI. I mean, I'm not on some scale, but let's say this happens. This is much further away. Okay. So, yeah, let's say for now the other one is, just to keep matters a little simple, the other one is very far away. Okay, so right, so basically what happens is that there is some kind of hysteresis, right? So this region in between is called the bistable region. Okay, so if I start from here and increase the input intensity, what happens is I go on this curve, and if I keep increasing, once I go here, I basically jump. So this middle branch is unstable. Okay, so even though it's a solution, so this middle intersection point here, 1, 2, 3, the middle one here is unstable. Okay, which means any small fluctuation that occurs will immediately push me like up or down. Okay, so these are the stable regions. So if I start from a lower intensity, I remain on this branch, right? And then if I go up to this value and then try to cross this value, I immediately jump to here and then go from. And now if I come back on this path, if I now start decreasing the intensity, then I remain on this upper branch until I come to this point, and then I immediately jump down. Okay. So this thing is called like optical bistability. So it's something like a memory here. You're getting two stable states, right? And which state you are in depends on the history, right? How you arrived at that. So your input intensity could be I1, but for the same intensity, my output could either be this I3A or I3B, and which one it is depends on whether it came from a lower intensity or higher intensity. So basically, nonlinearity causes the system to have this kind of memory effect. In the linear case, if you don't have any nonlinearity, you know that Fabry-Pérot has this constant response, right? For every input value, you have a one output value. But as soon as you introduce Kerr nonlinearity, then you start getting these bistable solutions, right? And you can use this now for optical switching, for example, right? So let's say I sit here, right? So my input intensity at some particular value. So I came from a lower side, and then I have some input value. So my output is at this state, and then for a very small change in my input intensity, my output will suddenly jump to this upper value, right? So very small change in input will give me a large change in my output. And ideally, like if you want to use this as a switch, for example, turn the output on and off using the input, then what you want is this region to be very thin, right? So ideally for switching, you want something like that, right? So this region is very thin. So one state could be here, and the other state could be here, right? So let's say this is my 0 state. So I3 is 0. And so this will correspond to some input intensity I10. And the other, this one could be I31. And this is I11, right? So for a small change in my input, I get a very large change in my output, right? So if I have some signal like this is I10, this is I11, then the output will change by a much bigger amount. This is I30 and I31. Right. So some of you who are familiar with electronics or transistors, this looks similar, right? So this looks like a transistor action where, so an electronic transistor, there are a terminal called base. So in the base, you give a very small current or voltage, and at the output collector or emitter, you get a huge current or voltage. Okay, so I hope that's clear. Right, so I mean, initially when these kind of effects were discovered, it was very exciting. People thought, okay, we can make like optical memories, right? And very efficient optical switches, etc. But turned out practically just to make these devices and then scale them up to hundreds and thousands of devices interconnected with each other was not an easy task. So this kind of all optical computing didn't really take off. So mostly these kind of things are done in isolation in research experiments. But sort of there was a goal of trying to replace electronics with photonics or just optics, which didn't really or hasn't materialized till now. But some of these things were the ones which got people excited. Okay, so there was one question on how, okay, like if, so remember when we were looking at these intersections, what if it starts intersecting the other next resonance, then you'll get multiple, you might get even more solutions, right? And so then it starts becoming really complicated, right? So we look at a case where you can get really complicated dynamics. So I hope it was clear so far. Any questions on this optical bistability? So we'll see basically how this kind of system with nonlinear medium inside a cavity can give you much more complicated nonlinear dynamics and eventually lead to even chaotic solutions. Okay, so basically you lose all predictability of what's going to happen at the output because the dynamics become so complicated. Okay. So before we look at that, just want to quickly discuss how fields get transformed at a beam splitter. So beam splitter is a half silvered mirror, right? So basically, so it has 4 ports, 2 input ports and then 2 output ports, right? So E1, E2, E3, E4. And we want to just derive relations on how E3 and E4 are related to E1 and E2, depending on the reflectivity and transmission coefficients of this beam splitter. Why we are doing this is the model. So we look at one model of a nonlinear medium inside a ring cavity, which leads to chaotic dynamics. For that, we need, I mean, it will have beam splitters inside it, and we need to see how beam splitters transform the electric field amplitudes. Okay. Like for the mirror, it's straightforward. We just took some amplitude reflectivity small r, transmission reflectivity small t, and then the square of those were the intensity reflectivities, right? But here there's a subtlety that there's some phase relationship also, which is important. So I just want to, and this will be useful probably for you in other things you do in optics also. Okay, so then, so let's say, so this is some beam splitter. Okay, which has so reflectivity and some transmittivity. So these are the intensity, reflection, and transmission coefficients. So R plus T is 1. Right. So for example, a 50-50 beam splitter is, it'll, if I send in some power from one of the input ports, then it will send 50% on one side, 50%. So 50% is reflected, 50% transmitted. So those are the R and T. Okay, so, but we want to look at how the electric field amplitudes transform. So I can write E3. So E3, the one of the output ports, is the field E1, which is the fraction of the field E1 which is transmitted. So that's, let's say, some small t times E1. And it will also have, if I send in E2 from the other side, it will have the reflected component of E2. So that's R times E2. Right? And of course, so mod of t square will be t, and mod of r square will be r, right? But what we'll end up seeing is that basically this r is not, you can't just take it as square root of r or square root of t. There'll be a phase involved. So t and r will have some phase, like there'll be some phase, there'll be some, so it will be a complex number, not just a real number which is square root of t or r, which for example we could take for a mirror, right? Similarly, E4, I can write r times E1 plus t times E2, right? So E4 is r times E1 and t times E2. Okay, so I can write this relation in a matrix form. So E3, E4. Right, so E1, E2 is my input ports, and then E3, E4 are my output. Right, and how they get transformed is this matrix here, which is the beam splitter matrix. Right, so this is E out, E in. So now if you have a lossless beam splitter, which usually would be the case, right? This is some very thin piece of glass. So there's no loss in the beam splitter, which means the total intensity going out is the total intensity coming in, right? Which just means what? That mod of E3 square plus mod of E4 square. That's the intensity going out. Is equal to mod of E1 square plus mod of E2 square. That's the intensity coming in. Right, so this thing I can write in matrix form like this. Right, so like a row matrix you are multiplied by column matrix. You can see the multiplication of this will give you this. Right, and what is this? This is the conjugate transpose of this, which is just also known as the Hermitian. Okay, so this sign denotes Hermitian. It just means conjugate transpose. Right, so when you take a Hermitian of a matrix, you take conjugates of all the elements and then transpose. So, right, so that's the left hand side. Similarly, the right hand side, forget about that. So, now what we can do is we can use these relations. So, we can write E3, E4 in terms of E1, E2, right? So, we just plug this thing here. So, that will give me summation of this times this, right? And now we have a product of two matrices, and we want to take Hermitian of that. So there is a So there is a relation for matrices. So if you take, if A and B are two matrices, and you take the Hermitian of A times B, it's equal to the Hermitian of B times Hermitian of A. You might have seen this in other places. So we can use that rule here. So this becomes E1, E2 Hermitian, then Hermitian of this TRRT, right? And maybe I'll write it first. Okay. And what do we want this to be equal to? So remember we started from mod E3 square plus mod E4 square. That's what it is. And we want that to be equal to mod E1 square plus mod E2 square, right? Which is just E1, E2 Hermitian times E1, E2. That's mod E1 square plus mod E2 square. So basically this thing coming in the middle should give me the identity matrix. Right? So if this thing coming in the middle gives me the identity matrix, then this just becomes identity and I just get this times this. Right? So then the condition that we want is basically this, right? And then the transpose of this is simple, right? You just take conjugates and then transpose, but when you transpose, nothing happens because, yeah, like the row and column are the same. So it just becomes conjugates here. Okay, so now the product of these two should give this. So we can just go element by element. So the first element here would be T conjugate T plus R conjugate R should be equal to 1. Right? So first condition is, but yeah, so that we already know, right? This just means which of course is expected for a lossless beam splitter, right? The transmitted and reflected intensities should, or the transmission and reflection power coefficients should add up to 1. Right, but to then get another condition, so now, so look at this second element which needs to be 0, right? So that will be T conjugate R plus R conjugate T, and that needs to be 0. So the second condition is okay. So without loss of generality, we can assume, so in general we have two complex numbers. So what we can say is, okay, we can assume one of them to be real. So let's say assume T is real, which means T is equal to T conjugate. Right, so then I can just take T common out here. And I'll get R plus R conjugate equal to 0. Right? And R, so let me write it as mod of R times some e to the I phase. So then this will give me 2 times T times mod of R, and then I'll get e to the I phi plus e to the minus I phi, which will give me cosine phi equal to 0. Right, so basically, so T and R of course can't be 0, otherwise it won't be a beam splitter, right? Both of them have to be non-zero. So then the only condition remaining is, so the angle has to be such that cosine phi is 0, right? So we can choose phi is equal to pi by 2. Right, which means what? That R, so here is e to the I pi by 2, which means there is an I. So if I take T to be real, then R has to have a iota in front of it, or a pi by 2 phase shift. Okay, so in other words, if I want to write the small amplitude coefficients in terms of the power coefficient, so I can write T as square root of T, but R I have to write it I times square root of R. So I have to take this I can't just, right? In other words, there is a pi by 2 phase shift between the reflected and transmitted amplitudes for a beam splitter, right? Which may not be obvious in the beginning when you just look at it, but yeah, so it's actually very important. So the beam splitter matrix transform matrix. So of course this is not unique, right? So I just got some conditions that, so I assume T to be real, and then I got a condition on the phase for R, but you could, for example, choose both T and R to be complex numbers, and then try to satisfy those relations, right? So this is not unique, but whatever relation you choose, basically physically, you'll see what is happening is there's a pi by 2 phase shift between the reflected and transmitted. Okay, so the mathematical form that you can choose is not unique, right? So here we chose T to be real, and then we got R as I times this, but you could choose other forms also that satisfy that equation of T conjugate R plus R conjugate T is 0. Okay, so this beam splitter transform matrix then becomes, so I have T or square root of T, I times square root of R. Right, so that's the beam splitter transform matrix. So these I's are very important. And in some other fields like quantum optics, you will see that these actually give rise to some very funny features, some counterintuitive features in quantum optics, for example. So for the very popular case of a 50-50 beam splitter, then T and R are 1/2. So then this matrix is 1 over square root of 2. Okay, so as I said, so this form of the matrix is not unique, right? You could choose some other combination. So the in some places you might see a different form for the beam splitter matrix, but these phase relationships have to hold. And yeah. Anyway, so the point I wanted to make was this: including iota is necessary for a beam splitter. Any confusion regarding this? Hope it's clear. Okay, so now we look at a specific setup of a nonlinear cavity, which is called the Ikeda model after Ikeda and colleagues who first sort of described and observed these. Okay, so this is basically a curved nonlinear medium in a ring cavity. A ring cavity is also known like a traveling wave cavity, right? So this Fabry-Perot cavity that we first saw, the field inside the cavity is a standing wave, right? But in ring cavity, the field inside the cavity is actually a traveling wave, it's not a standing wave. So the setup is something like this. So the cavity is made up of two beam splitters and then two mirrors. Okay, so the input and output is using beam splitters. So input field comes from here. So this is a beam splitter. This is also a beam splitter, and these two are perfect mirrors. Okay, so the field sort of comes in, goes into the cavity through the beam splitter. Then part of it reflects back into the cavity, part of it goes out. Then from the mirror they get reflected back, right? And then here they are back in. And so here, let's say I put a nonlinear medium. So it has some chi3 or n2, right? And the length of this nonlinear medium is some d. So these are 100% reflecting. Okay, and then let's say the total length of the cavity is some L. Okay, so again I have some input field here E in and transmitted field ET. And then some field inside the cavity EC. So
Sir,
again,
how do we know? How do we
yeah,
know that the field inside the ring cavity is just traveling wave? We do it mathematically, or we just uh,
yeah, I mean you can directly see, right? So the field here is circulating in one direction,
okay,
right? The field is only traveling in one direction. There's no field in the other direction,
okay, sir.
just from the setup, right?
Yes, sir.
So if I want to write the cavity field, right? So EC at some time t. Okay, so now I'm explicitly taking some time because actually what we'll see is that um, if you have the right parameters, then actually the cavity may not reach a steady state at all, even though you have a CW input field, right? So a constant input field or intensity. Due to the nonlinear dynamics here, turns out that the output never settles and it's always time varying. Okay, so that's why we're taking some t here. So that's P again. So the cavity field will have the part of the field which is transmitted through the beam splitter, the input field. So that's P times P in. Right? And then the part which travels through the cavity like this, right? So that will be the field which was in the cavity. So let's say it takes the photon TR to make this round trip, right? So the field at T minus TR, right? So I'm looking at the cavity field at time T at the current time, which will be the transmission times, let's say E in at the current time. But for a CW input field, then this is just a constant, it doesn't matter. And the field which was there one round trip ago, right, which went through this path and came back. So this was the field which was one round trip ago. So TR is round trip time. Right, so that's just be some like the total length of the cavity divided by speed of light, taking into account the speed in the medium, etc. Right, so what happens to this field in one round trip? Of course, it acquires a phase. So e to the I phi again. So this is the round trip phase. And then there are two reflections. So I mean there are four, I guess, from here, starting here, there are 1, 2, 3, 4 reflections. But two of them are from these mirrors which have 100% reflectivity. So that doesn't do anything. That's just it reflects the whole field, right? So you just multiply by 1. So you just have to take into account these two reflections are the two beam splitters. And we just saw that reflection from a beam splitter, in the amplitude you have to multiply by I times R, right? So you multiply by I times R 2 times square of that, right? So we took T here. So for the beam splitter we took T, for the transmitted a real number T. So for the reflection I have to take I times R, where R is the real.
But that earlier field is also transmitted, so there should be T in front of it.
Which earlier field?
So EC, because that is also transmitted by the initial beam splitter.
No, I want to see what is the field here inside the cavity.
Okay, sir. I got it.
Right, that is the field which was there one round trip ago, which got reflected from the beam splitter here, reflected from the mirror, reflected from the mirror, and then again reflected from the beam splitter. The one which transmitted left the cavity. So that will come in ET or something, but not in EC, right?
Sir, I
Okay,
was saying that should be common, transmission coefficient should be common here. Or it's just
sorry?
in front of, the transmission coefficient should be common in both the terms. It should be just in front of input electric field, or it should be present on both sides, in both the terms.
No, so here why would there be a T? There should not, there won't be any T here, right? So I'm saying how is the cavity field at time T related to the cavity field at time T minus TR? That's just a phase and these two reflections, right?
Okay, sir.
Why is there so there's a reflection from a beam splitter here. These are reflections from mirrors which don't do anything, and then another reflection from a beam splitter here. If it was transmitted through either of the beam splitters, then it will leave the cavity. Right? If it got transmitted here, then it will leave the cavity, or if it got transmitted here, then it will leave the cavity. It won't contribute to EC.
Okay, sir.
Okay, so So this is the two or reflections from two beam splitters. Okay, and so what is the round trip phase phi? That is again the sum of the linear phase plus a nonlinear phase. Right, so the linear phase again is just let's say whatever linear refractive index, if this has some medium, or if it's just free space, then n0 is just 1, right? So k times L. You could also include the linear phase shift through the medium, but let's say d is much smaller than L, so then the linear phase is just that, and then the nonlinear phase will be acquired through the nonlinear medium, right? So that will be omega over c n2, and then I will be the cavity intensity IC, and that will be again at T minus TR. Right? So we are saying that the cavity field at T minus TR acquired this phase phi. So that phase has to have the intensity of this field. If some of you, can you all please mute your mic? There's some background from someone. Uh, so is this clear? So the intensity here is basically the intensity of this field. So at T minus TR, because that's the field which is acquiring the phase. Okay, times the length of the nonlinear medium D. Okay, so this intensity is basically again this 2 mod of EC at T minus TR squared. Okay, so basically the nonlinear phase is related to this cavity field like this. Okay. Yeah, so the main point is here that the field here should be T minus TR, because that field is acquiring the phase. Okay, so we can normalize the field. Yeah, I have to erase this. Okay, so we normalize the fields like this. So the input field, the cavity field, and the transmitted field. We define some new curly E, which is the actual electric field, divided by this constant which is coming here, just to make the math a little simpler and see what's going on. Okay, so these are some normalized fields. So I can write this equation in terms of the normalized fields. So EC at, now I say N, which is the time at nth round trip, right? So, or in other words, n is t over tr. Okay, so I'm looking at the field after every round trip. So after the nth round trip, so the first part is again just the transmission through the wave splitter of the input field at the same time. And for the second term, this I square will give me a minus sign. That's the minus sign here. And then I have EC of t minus tr. So in the time units of per round trip, that's n minus 1, the previous round trip. And here the phase will be some e to the phi naught is the linear phase plus this mod of EC n minus 1 square. Right, so this curly E I defined as this square root of this times E, so this phi NL will just be the mod of curly EC square. You can see. Okay, so this is sort of the dynamical equation or the governing equation for that kind of cavity. So, right, so basically we start from some n equal to 0 time. This input field could be, let's say, a constant which is always on. So in that case, EI of n will just be some constant for all n. And then you can just see how the cavity field is evolving, right? If it reaches some steady state, eventually then EC after some n will reach a constant value. Okay, so those are called stationary solutions, steady state solutions. Or time independent solutions, right? So stationary solutions will be, so eventually EC of n becomes independent of n. Right? So in other words, so let's say if I'm plotting this E of C as a function of n, let's say initially there are some fluctuations, but eventually it sort of settles to a constant value. Okay, so after some initial settling time, it just becomes a constant. Those are called stationary solutions, right? So typically that is what you would expect, for example, for linear systems, right? For a constant input, my output has to be constant. Even for the bistable systems that we discussed, eventually the output is constant, right? Depending on which path we took. It could be one of two values, but it's finally constant at some particular value. But in this model, turns out sometimes you get these stationary solutions. Okay, but not always. So again, for stationary solutions, you can. So first, another way to look at stationary solutions, the EC of n is equal to EC at n minus 1. Right? It's not changing after after every round trip. So in the equation here, I can just put EC of n is equal to EC of n minus 1. Right, so from here, you can write EC like that. You can see now it looks similar to the case we had for the optical bistability. In terms of intensity, so if I say IC, which is proportional to mod EC square, so then IC over I input. You can see is E by right. So IC over I in again it goes something like 1 over some constant plus cosine in the argument. Again, you'll have IC. Okay. So in particular, for example, if let's say the round trip phase phi naught, this is the linear round trip phase, right? So here if phi naught, let's say is pi, let's say my or some odd multiple of pi. Right, let's say I've set up the cavity length such that you can see then this term becomes so you get pi plus something. So that's cosine of pi plus something is minus of cos, right? And then it becomes same as what we had for the bistability case in a Fabry-Pérot cavity. Okay, so for this, you can see that IC over II becomes the same thing that we had. Okay, so again you have IC here and then IC in the argument. And then the transmitted intensity, if you want, is just through the cavity field transmitted through the beam splitter. Okay. And basically, again, this will have solutions like what we saw, right? So depending on the number of intersections, you could have branches where you have multiple solutions. So this is IC or IT as a function of IA. Okay. And again, some parts of this will be unstable. Some parts will be stable. Okay. And it can get quite complicated. But basically, if there is a solution to this thing, so you'll be either somewhere on this point, somewhere on this graph, then you'll get the stationary solution corresponding to that solution. Okay. So if your input intensity is in a range where you have a stable solution, right? So this region or somewhere here, then you can get a stationary solution where the output is also constant for input constant. But in this complicated case, it turns out that there are regions where the solutions are, there is no stable solution. Okay, so there is some range for I in where there is no stable solution. Okay, all the solutions are unstable. So in that case, what happens is basically you never get to this stationary state. And after each round trip, the field keeps changing. Right? So even for a constant input intensity, the cavity field or the transmitted intensity will keep fluctuating with time. Okay? And it's coming just from it's not coming from any randomness or any unknown fluctuations or anything, right? It's just coming from a deterministic equation due to the nonlinearity. Okay, so let's say one way to analyze these solutions, right, is what you do is, so you choose some particular input intensity, and then you just measure the cavity field or the transmitted field at, let's say, every a time corresponding to every round trip. Right, so for a particular input intensity, you see how this cavity field varies, and eventually, so you wait for some time, you wait for some initial time, and then see for the initial any transients to settle down. Okay, so and then look for some long n. Right, so finally, if it goes to some constant value, those are stationary solutions. So that will happen for some particular values of input intensity. Let's say typically initially, when you start from low values of intensity, initially you'll have stationary solutions. Now as you start increasing, first you'll get another branch. Okay, so you'll get to this sort of bistable kind of region. Okay, so there'll be a certain range of intensity where you will see that. So again, we wait for some initial point to settle down, and then after that point, basically it sort of oscillates. Between two values. Okay, so this is n plus 1. This is n plus 1, n plus 2, n plus 3, right? So it's switching between two values. Let me say this is intensity. Okay, so this is not a steady state solution. Okay, remember my input is constant CW, but my now output is periodic. Right. So one way you can look at these dynamics is what is called, so these time dynamics. You can represent them on a phase plot. Okay, so what is phase plot? So of course at every point I have a solution for EC, which in general is a complex number, right? So it has an amplitude and phase. So what I do, I represent it on the complex plane. So real part of EC and imaginary part of EC. So for every solution, I put it on the complex plane. Right. So for a stationary solution, for a constant solution, I'll just get 1 point. Right. Whatever the output field is, and at every instant, I'll keep getting that point again and again. Right. So in the phase plot, if I just get 1 point, that's a stationary solution. right? But for this kind of thing, I'll get 2 points, right? So for example, this would be for even values of n, and this will be for odd values of n. Right? So it will keep going back and forth. So if I plot all the values that I get on this complex plane, I get 2 points, right? So this will be a periodic solution. Okay. Now let's say you increase intensity a bit further. Now you start getting more branches into the picture. Okay. And the next kind of solution that can be observed is a periodic solution with a larger period. Okay, so then let's say you have some 4 values, 1, 2, 3, 4. It goes like this: 1, 2, 3. Then it comes back: 1, 2, 3, 4. Okay, so now the period is, instead of 2, now it's 4, right? One, two, three, 4. Okay, and then it repeats. So now the period is 4, and I have 4 different values of the output field. So in my phase plot, I have 4 points. Right? So it will go from like this, for successive values.
Sir, can you explain the phase plot again?
So phase plot is, so I have some tiny series, right, for my output field. So I take the value of the field and then just represent it on the complex plane, and then do it for all values of time. So if I have a stationary solution, which means a constant solution, then all of them will lie on the same point. So I'll have this 1 point, right? But now let's say if I have a periodic solution, so it goes high, low, high, low, high, low, high, low. So there are 2 points, 2 distinct points, which will occupy 2 different points in this complex plane because they have different values of the field. But all the points will lie on one of these 2 points, right? So what I'm doing is here is, so computing this field from, let's say n equal to, so I wait for initial sum dynamics. So let's say I start from n equal to 1000, and then compute the field for all values till, I don't know, 1, like 10 to the 5 or 10 to the 6. See what the field looks like, and then for each n, I put the EC I get on this complex plane.
Okay, sir.
Right? So if I have a steady state solution, which means basically I'll get all the EC at each n to be the same, I'll keep putting the same point again. So I'll just get 1 point. Right? If I have a periodic solution, I'll have 2 points. So I'll put this, everything will either lie on that or this, right? So I'm saying, as in such a model, when you start increasing the intensity from some low value, initially you get stationary solutions. So in the phase plot, you'll just have 1 point. As you increase the intensity, eventually you will go to a periodic solution with 2 points. As you increase the intensity further, you'll see this period doubling. So you'll get 4 points. So now you have 4 distinct values. So the period is now 4. Okay. So this is called period doubling. So you can imagine what happens now. Like if you increase intensity further, you'll see 4 more points pop up here. Okay, and the field will look now. So it will take 8. So it will repeat after 8. So now this thing will repeat again. Right? So it looks more and more complicated. Right? So the more points you have in your phase plot, the more complicated the time series is. But as long as you have a finite number of points, it's a periodic solution because and the period is basically the number of points, right? Because you're only getting those points which repeat, right? So yeah, and you keep increasing, you get more and more points, more and more points. Okay, so eventually you'll reach a stage where this thing doesn't look anything like a finite set of points anymore. It just looks like some strange figure here. So as you add more and more points, so as you look for longer and longer times, you will add more and more new points. Okay, but they'll all lie in sort of a certain region, but they'll all be distinct. Okay, so this will become dense. It won't be a finite set of points anymore. So this is the region of chaos. Right. So here basically you lose the ability to predict. So as long as I had a finite set of points, I could sort of say, okay, it is the field value is either this, or this. It's one of these values, right? And depending on how this periodicity varies, I can say, okay, if it's at the first point of the period, then it's here. If it's second here, third here, fourth here. But eventually, once the intensity gets to a certain range, then basically you don't know where you are. Okay, so there is no way to deterministically say what your output intensity is, even though your input intensity is a constant number. You know very well, and you know everything about your cavity, length, nonlinearity. Everything is deterministic, but you just lose the ability to predict the output. Just from the complicated nonlinear dynamics. Okay, so this is called chaos. So chaos is a system where long-term prediction becomes impossible just due to, even though your system is deterministic.
So we can say that chaos is due to a large number of fluctuations.
Large number of so there are no fluctuations as such here, right?
Yeah, the period is long, that's why it is occurring.
No. So eventually it goes to an aperiodic state that it doesn't repeat.
Okay.
So you can show that in the chaotic state, it's in that sense it's aperiodic. It doesn't repeat.
Okay.
Right. So another way to represent this is basically if you look at so let's say I'm plotting here EC. Could be, let's say, the real part or the imaginary part or the, let's say, the modulus or something as a function of my input intensity. Right. So for some low values of intensity, I'll get a stationary solution, which means I'm only getting one value of the cavity field for each value of input intensity. Okay. And so I lie on this one curve for a certain time or for a certain range of input intensity. Then as soon as I exceed a particular threshold value, I get into two branches. So I get a periodic solution. Right. So for example, for this particular value of the input intensity, I have two values of EC. So it's periodic solution between these two. Now as you keep increasing further and cross another threshold, this splits into two more. Now I have 4 branches, right? So here you have stationary, this is periodic or period 2, this is period 4, right? And eventually this keeps doubling, okay? And this doubling keeps happening now, like closer and closer, right? And eventually, basically, you reach a threshold after which this is totally dense. Okay, so period keeps doubling until you reach a regime. So beyond a certain threshold intensity, this is the chaotic regime, right? So this is now a continuous band. So it could be anywhere here, and it's basically impossible to tell at a particular point in time, at a particular n, where will you be in this band. So of course it's a deterministic thing, right? So for example, I could deterministically compute this thing, right? So let's say I want to see what the field value will be at n equal to some 10 million. Then I start from n equal to 0. I know all these values exactly, right? And I can just keep churning. And of course, I can compute what is EC at 10 million, right? So in that sense, of course, it's deterministic, right? It's not that. But the point here in the chaotic state is if I change this E in, for example, by, let's say, 1 part in 10 to the 9 or something. Okay, some very, very, very small. So in the 9th or 10th decimal place, I change 1 digit and then recompute this starting from n equal to 0. You'll see that EC at 10 million that you get will be very different. Okay, so let's say in the first case, I got this point here, that value of EC. Now I change it by 1 part in a billion or something, and then do it again. I'll land up somewhere here, which is very different. So this is called the sensitive dependence on initial conditions, right? Which is the essence of chaos, basically. So in the time dynamics, what is happening? So if I look at EC versus n, so I start from a particular value and then have some dynamics. So now I change the initial conditions by infinitesimal amount, like really small. So initially, it's almost, you can't see any change, but eventually it starts diverging. Okay, and for long times it now becomes completely different. So for long time, like even though these two initial conditions, let's say, were so close together, let's say beyond or below the resolution of our measurement, eventually they diverge so much that I can't predict now, like whether I'm here or here, right? So in that sense, you lose predictability, right? So because I have a deterministic equation, of course, everything is deterministic, but I need to start from some value, right? Now, how precise do I choose this value? Should I say, okay, 1.00001 is enough, or 0.00001? But even if instead of 0.001, if I take 0.002, there will be a huge change in my output. So unless I know my initial conditions absolutely perfectly, which is sort of not really possible, then I lose predictability for long times. Right? That is chaos. And basically, what this showed was that in a very simple optical model, right? So typically, chaos required certain complicated things. So, for example, chaos is famous in weather systems, right? In meteorological systems, where we keep making fun of these weather forecasters who always seem to get it wrong, right? The reason it's so hard is because it's a chaotic system, you have a lot of different variables which are coupled to each other in a nonlinear fashion. Okay, so initially a lot of the advances in chaos were done in atmospheric sciences and weather. Okay. But basically, you need a system of some coupled nonlinear equations to typically see chaos. But here, basically, what Ikeda and colleagues showed was this very simple system, right? Just have an optical cavity and a chi-3 medium inside, and with that, you can see all these complicated chaotic dynamics. And they were even able to show it experimentally. I think, yeah. So, right. So chaos. So this nonlinear dynamics and chaos is a whole field in applied mathematics in itself, right? So there are entire courses devoted to that topic. So there are a lot of more details here, which yeah, I mean you can eventually go into if you are interested. But here we just want to show that a simple optical system can lead to very complicated dynamics and even eventually chaos. So yeah, and this coming back to this phase plot. So in the chaotic region, the phase plot looks very complicated. So, okay, initially you might expect that in the chaotic regime, basically your phase plot just looks like complete noise, right? Like you could get random points anywhere in the complex plane. So it just looks like some random noise. But turns out each chaotic system actually has a particular feature. Okay, so these patterns are not totally random. They have some sort of feature to it. So it looks like some spiral or some. But it's not a deterministic spiral, that's the point. So it's not like something like this, where all the points lie on this curve. Right? It's some dense collection of points which lie in a certain region. All of them will be close to each other here. And this thing is called the strange attractor. Okay, so these are all chaos theory terms, basically. So if you take any chaotic system and you plot this phase plot, it will be some strange. So it's called strange because it typically looks some strange. It's called an attractor because all the solutions are lying on this attractor, right? So you don't get any solutions away from this. So there are blank regions. So it's not like your solutions are spanning the entire space now. But this thing is not like a smooth curve or anything. So for example, typically these have what are called fractal dimensions. So if you blow a small region of this thing up, it will sort of look a zoom. If you zoom into a small region, it will look as if you have the original figure again. Okay, and then you can take another portion of this and zoom in again, and you'll again get that. So that's a fractal. I mean, I'm sure you must have heard about that term, fractal, right? So these strange attractors typically are fractals. They have fractal dimensions. Yeah, so a good exercise would be, so yeah, maybe in the next homework, you can easily do this on your own laptop, computer and see, right? So you just have an equation that you start from n equal to 0 and run it for some time, and then change for different parameters, see how this varies. You can plot phase plots, and it's a very good exercise to see this for yourself. So maybe in the next homework assignment, I'll have one question like this. It's really fun to.
So did chaos have something related to quantum mechanics?
So there is, so all this is classical, right? So the traditional nonlinear dynamics and chaos theory is all in the classical domain. But there is a new, or there's a recent field, or fairly recent, I guess, not very recent, but of quantum chaos also, which is looking at chaos in quantum systems. Okay, and basically where those things are, so these are all classical systems, right? We are looking at classical. So there, what people are looking at is you take a quantum system, which is described by some Schrodinger equation, and then depending on, for example, the potential or something, can your energy levels or eigen solutions start becoming like chaotic or something, or some trajectory uh, in a region of space or in a potential well, can a trajectory start becoming chaotic or things like that. I mean, one interesting thing is also this very sensitive dependence on initial conditions, right? So from quantum mechanics, we already know that we can't define a quantity to better than some precision given by the uncertainty limit, right? So you have delta x, delta p greater than h cross. Similarly, so for an electromagnetic field, you have a relationship between the field values also, right? So the field amplitude, so the x and p get replaced by what are called field quadratures. So you can think of them something like the cosine omega t part and the sine omega t part. Those become operators, and those are also related by uncertainty relations. So in essence, what I'm saying is you can't measure the field very precisely. There is uncertainty relations in the fields also. So you can't measure an electric field beyond a certain precision fundamentally from quantum mechanics. So that would again mean that fundamentally you can't have this very precise. So eventually it will, right? So, so this, I don't know if people have explored, or I mean, I'm not an expert in chaos theory or anything, but I guess that's an interesting thing, right? So precision fundamentally is limited by the uncertainty relations of quantum mechanics, and any small imprecision in the initial condition gives rise to chaotic dynamics. So if you have a system which somehow is sensitive on this quantum scale, right? Could just fundamental quantum mechanics forbid you from predicting the outcome? Or that's an interesting question. I don't know if it's been typically most of the times people look at these imprecision initial conditions classically, that basically we can't measure based on the precision of instruments available to us, etc., a quantity beyond a precise value. But of course, fundamentally, even from quantum mechanics, even if you had perfect instruments, then you can't measure it beyond a precision, right? So, so I don't know that interplay, how much of that has been explored. So, based on the uncertainty relation, if this is now slightly different value, how does that yeah, in a chaotic system, what does that?
Okay, sir.
But certainly, the field of quantum chaos is now sort of expanding with more people interested in that. But as I said, some of those people are just looking at so this kind of thing in a quantum system. So instead of a classical system, you have some quantum system, and you're trying to see chaotic dynamics in that. Yeah. So, but yeah, this is a whole big field, as I said, on its own. But with the simple system in optics, we can learn some of those most important features of chaotic systems already.